Okay,
Okay.
I think
Work.
I think it's working now, and assume that you can see the screen here. So the title is Diffusion Model for Stochastic Parameterization, a case example of numerical precipitation estimates. As you mentioned, I'm currently working at Chinese Academy of Science. Previously, I was working at Lawrence Livermore National Lab, like working on combining deep generative models and dynamical models to improve the forecast across weather to climate scale. And here I'm basically continuing what I have been doing in LNL. And previously I was trying something like a variational autoencoder and GANs, but now I think that there's a game changer coming. So I will tell you why. I always enjoy start a presentation with the following big picture, that is what we have achieved through the past 150 years in the field of climate studies. So all these things start from like the beginning of 18th century when we first collect use electric telegraph to collect weather data, and we extrapolate those data to give us some weather forecasts. And gradually, Birknes developed these equations that govern the atmospheric dynamics. And then Richardson said that maybe we can try to solve these equations by hand using numerical methods. So he did the first try, but did not success. And in 1945, von Neumann tried to solve these equations using the first electric computer called ENIAC. And Giuliani developed the so-called Chinese report telling us what we should do in the coming 70 years of this field. That is basically trying to develop more complicated models that include more different components, trying to describe different spheres of the climate system. And with the advancement of satellite remote sensing and the new computing techniques we have, we can now resolve the equations to a finer and finer resolution. And we also have different observations giving us the initial state. But we realize that it's a chaotic system and we don't know what will exactly happen in 15 days. But we still try to predict the climate, and we have the CMIP project. And I think there's a very fine picture here in the CMIP project that telling us the three key uncertainties in climate prediction. One is called systematic bias, which comes from the model we have, and the other is the representation to forcing, which tells us it's kind of aleatoric uncertainty. We don't know what will happen, how much greenhouse gas we will emit to the environment. So we don't know the exact future, the forcing. And the other is called variability, predictability. I think it comes from the chaotic nature of the climate system. That is, a very small initial state perturbation would give us a very different results in a very short period of time. So basically, I think climate science is trying to disentangle these three kind of uncertainties: model systematic bias, internal variability noise, and the forcing or the representation of the forcings. But I think we are kind of bottlenecked here as the models become more and more complicated, and the observations coming from different sources are trying to blur the way that how we can see clearly the exact picture of this system. So there's something called machine learning that come into play because we think that maybe our human intelligence is not enough for us to keep improving this complicated observation and simulation system. And there is a kind of like a buzzword called AI for science, and we use artificial intelligence or exactly machine learning to do science. We have the following things to do. One is to explore or control like different experiments, and the second is to fill in the missing parts or fill in the like coarse-grained things. And third is to do computation acceleration. Maybe we can use Fourier neural operator to accelerate the numerical models like what they did in NVIDIA, but now they use graph casting DeepMind to do weather forecast. And the fourth, maybe it's more straightforward, is to do inverse modeling. We have the DNA figure here. They have different forms. Once we get this kind of structure from this kind of a picture, we know that the DNA is like this, and they won the Nobel Prize. But for now, we just took pictures of all the structures and get their figure here, and then we can do the inverse modeling to see what kind of figure would result in this kind of structure. And we can do some kind of inverse modeling, try to calibrate the parameters or trying to like see what kind of scenario give rise to what kind of results. And the final thing is called automated scientific discovery. Actually, we have done it like 100 years ago. Whitehead and Russell, they developed this Principia Mathematica, trying to say that if we have all the principles, can we have all the mathematical results? But actually, we don't. But still, we can know we have a lot of endeavor that trying to push this way forward, like Stephen Wolfram's physics project. And also there's something called adversarial learning. I think is pretty promising. That is, we may have a game between a bias detector and a bias corrector and post them in a like adversarial game. I think you have a paper having similar idea published in Nature Machine Intelligence. But before that, we do have a paper published in James Journal of Advances in Model Learning Earth Systems. And we try to formulate the GCM bias corrector and GCM bias detector and bias corrector, these two players in a single game, and see if we can correct GCM biases in a systematical and automatical way. This is AR for science. And regarding climate science, we do have many existing applications. One is called inverse modeling, and we do know that climate models have a lot of parameterization schemes, and each parameterization scheme may have different parameters, and we don't know which parameter give us the best results. So usually we do weather reforecast or do climate forecast to infer how the parameters influence the outcome of the climate models. But this usually takes around 10 to the 5th power of running for these climate models, and we cannot afford that. So what we can do is that we just sample some parameters, and we can get their response surface. That is how these parameters influence the mean behavior of these models. And we build a surrogate model trying to emulate how these parameters influence the model results. And we can use standard Markov chain Monte Carlo to sample all those parameters, which is pretty fast. And the second is to do parameterization. We know that climate models are not fine enough to resolve all the geophysical fluid processes. So what we do is that we have the resolved process as the input and put them into some semi-empirical functions to infer the impact of the unresolved processes on the resolved scales. And we have a lot of empirical equations, but it turns out that some data-driven solution might offer better results, like this kind of convection parameterization and this boundary layer parameterization. And the last thing is to accelerate the existing model, or try to replace them. Like we can do it using the transformer structure, digest the whole ERA5 data set, trying to see how the previous hours circulation field would give us would yield the next hour's circulation field, and we do it like using an autoregressive manner. Or if we do like more carefully, we can use this kind of icosahedral meshing to further discretize the geo field, and then use this kind of model to predict the weather. It can be pretty fast. And the last is about nowcasting. We know that the reason why we cannot do really good forecast is that we do not have a good initial state estimate, and second, we do not have a very good model. But if we just take into input of the radar reflection images and we put them to predict the next few hours precipitation, it turns out that we can achieve the best result here. So that's what we do here. But I think most of these things are like using a supervised learning manner, or if it's science, we know that we usually say that it's a control experiment. We have a well-developed experiment where we want to know how one factor influences the other factor. So it's called supervised learning. We can take into input of the predictor and try to infer the results of the predictant. But I think that for climate science, it's a chaotic system. It's very high dimensional. Usually we cannot design such good control experiments, which means that we don't have a good environment telling us how one factor exactly influences the other factor without changing all the other factors. So I think this formula might give us a better, allow us to better apply data-driven models or to use machine learning. This is called probabilistic machine learning. That is to use machine learning or exactly deep learning tools to estimate some unknown probability distributions. And here, if we recall these three uncertainties in climate science, that is model systematical bias and forcing, the other is the internal variability noise, we can put them into this single framework that is for different models, or we take reality as another model. There is something that we care about and how they influence the predictant. And we get all those data from different sources, like from simulations or from different scenarios, and infer how one predictor influences the predictant. And we have a learning machine. The learning machine is denoted as capital theta. It can be a deep neural network. It can be a diffusion model. It can be a transformer. And theta is the parameter that we need to learn. And in this way, we can know, we can digest all these different data and apply powerful deep neural networks to get something that we want. And the resulting entropy of this probability is the internal variability noise that is left after we control X here. And I think this formulation, although very simple, can serve as a foundation model in climate machine learning, just like the stable diffusion model you did into input all the images, and then giving a style, giving some text description, you can get the results of that. You can sample some image of that. And with this, we can see that for different climate models, for different forcing scenario, for different initial state, we want to know the distribution of the rest. So if we have a single model that take into input of all the CMIP6 dataset, maybe we can know a lot more about what they seek here. That is the forcing, the internal variability noise, and the model systematic bias. So that's a kind of a big dream. And I don't think it can be true before this year, because it has a lot of requirements which I'll dissect soon. But I think maybe it could be possible in a very soon time. But before that, let's see something simpler. Let's see some classical machine learning applications in climate science. And then we find some classical models, and I will introduce the diffusion model. Maybe I don't need to introduce the diffusion model, but I want to introduce how we can apply it in some classical problems. So the first application about using machine learning in climate science is to do statistical downscaling. And here I'm referring to the task of inferring the unresolved precipitation process using the resolved geophysical fluid dynamics. We have been doing this for hundreds of years. First, we see the synoptic map, and we know that there is a cyclone here, so we know the characteristic precipitation pattern downside. This is called Bergen School cyclone model, which we learned it here in China, like in our middle school. But in dynamical models, we already have the numerical solver for this geophysical fluid dynamics. But the precipitation is represented by a series of parameterization schemes from cloud microphysics to convection. And what we did here is we crop out a synoptic scale map, and we have the companion precipitation field listed here. These are from observations or from some grid merged data set. And we have this convolution recurrent structure trying to take into input some useful inductive bias, like the circulation field are translational equivariant, and they're the state variable representing the state of the hydrogen materials, trying to infer precipitation. And we get really good results, like if we look at the correlation coefficient. And here are results for correlation coefficient at different resolutions for the continuous United States. And we can have a correlation around 0.74, which is kind of inspiring. But if you look at specific events like hurricane, you will see that it's like there's too blurry, and the results are hardly useful. And the other thing is about probabilistic forecast. Once we go beyond the weather scale, we have something like we have the chaotic effect would result us in a lot of different states that are, some of them are more possible, some of them are less possible. And we have these are these things frequently occur in subseasonal to seasonal forecast. And we can dissect the bias in subseasonal to seasonal forecast into these 4 factors. The first 2 are from the initialization. We may have we may not have the full picture of the initial state of the climate system, and if we use subcoupled ocean atmosphere models, we may have something called initialization shock. And when we run the model, we have the model formulation error. And when we do ensemble modeling, we have the insufficient sampling of forecast spread. This is called aleatoric uncertainty. This is called epistemic uncertainty. And if we want to apply machine learning to disentangle these 3 factors, what can we do? Well, we can do it like this here. We have X as the ocean heat content, D as the indicating which XY example pairs coming from which model. It may come from CESM or from GFDL model, but we just put them together and see if we can learn how different models differ in their way of how to encode the predictor, the probability dependency between X and Y. And we have, maybe preferably, we have a spherical convolutional neural network as our learning machine. And we dump all the CMIP 5, CMIP 6 models into this thing here and do maximum likelihood estimation. And once we get that, we may say that given the ocean heat content of the current year and given this model, what would its prediction look like? And the other model, what would its prediction look like? And if it's reality here, what would the future look like? So that's what we did. We try to put all this CMIP 5, CMIP 6 data into a single conditional generative model to make seasonal forecast. Actually, it's pretty good. And the third thing is to estimate the historical current climate state using limited data. We know that historical observations, they are not comprehensive because we do not have so well covered observation instruments. But it turns out that we can use something called partial convolution to get here from here, and it's really accurate. But 2 years ago, there's something called masked autoencoder. If they do not use convolutional structure here, they can learn the dependency between different places and recover the picture with like 10% of the information in this figure. And I think it's a good way to learn tidy connection or how one factor influences the other factor. But the drawback here is that this is still a deterministic model. And a member from my group is trying to develop this, to improve it to a probabilistic model, and to see that how two different locations are tightly connected, and how the knowledge of different locations might get us the knowledge of the whole picture. And I think it might be pretty useful in data assimilation tasks. And the other thing, as I mentioned, is that maybe we can try to see CMIP coupled model in the comparison project, which is here, like in the eye of a deep generative model. That is the foundation model idea. And the current CMIP, although they are pretty big already, they have 3 drawbacks. One is that they do not have sufficient sampling of internal climate variability noise, and they have ubiquitous model systematical biases, and they have insufficient exploration of possible emission scenarios. CMIP 5, they have 4 emission scenarios. CMIP 6, they have 6 to 8. In CMIP 7, can we have infinite many emission scenarios by doing interpolation between different emission scenarios? And we need fast generation of model ensembles, learn where model differs, and create representative emission scenarios. So if we consider all these 3 uncertainties together, maybe we can do it. But these have a really high requirement on the underlying probabilistic model. It's no longer trying to estimate the expectation of Y given X, but we want to know the probability distribution. And we know that this is a simple idea, but a simple but powerful idea. The difficulty is what should serve as this learning machine. Can we use the generative advisor net to do this? And probably the first thing to do is to clarify what the learning machine should be like. So it should have the following 6. It should fulfill the following 6 requirements. The first is that it should have realistic samples, so that all the samples we fit in here can have realistic log probability, so we can maximize accurately. And the second is that we want to have full coverage of the PDF. We don't want to cover part of it and run the model like iteratively, so resulting in something that's totally unreasonable. We want the model to cover all the modes here. And it's not fitting a static probability distribution. It's not like stable diffusion. We have all the images there, and we do not need to care about the condition. But in climate science, usually we do is that we have a condition, and for each condition, usually we only have one single realized sample of it. And can we still learn a flexible control of this condition? And the fourth one is scale adaptability. It's particularly proposed for parameterization. So for example, we know that the two holy grails in developing data-driven or in developing parameterization schemes is uncertainty aware and scale awareness. So it should work for different scales, like from convection scale to synoptic scale. And can we just take into input of a larger picture and have the model automatically depict where it should care about? And that's what we want the model to do. And the fifth one is fast sampling. We can accomplish this with numerical methods. We just keep creating a lot more ensemble members of the dynamical models, but that's too slow. Maybe we can do it faster. And finally, we want to have accurate probability estimate. That's for a task of climate change detection. That is, if a single model here and D is a single model's results coming from different emission scenarios. If we can know the exact difference between two probability distributions, where the only difference between these two distributions is the emission scenario from a dynamical model that creates these samples, then we know then we have a clear idea of how climate change influence the climatology influence the climatology. Here, the climatology is described by a very large dimensional probability distribution. And so given this task, that I always try to find the best model that we can use to march toward this goal. And what probabilistic learning machine should we favor? So there is a very classic tree for classifying different generative models, and part of them can fulfill part of these requirements, but no single one can fulfill all of them before this year, I would say. So in 2014 to 2022 is the era of generative adversarial nets and variational autoencoders. But since June of last year, there's a game changer here, and maybe it's the era of diffusion, because nowadays maybe we can fulfill all these requirements with a single model, and I will explain why. So I would try to describe and try to introduce the diffusion model in a very classical, very classical problem, still the problem of numerical precipitation estimation. I think to do downscaling or to do this kind of parameterization is the low-hanging fruit in climate machine learning. And if I'm not doing this, I believe someone else is doing it. And I know Stephen Rust might be doing it. I know Mike Pritchard might be doing it. So the problem formulation is as follows. We have the resolved dynamical field come from CFS reanalysis for the past 30 years. Is half degree hourly geopotential height, wind, humidity, temperature at different pressure levels. And we also take into input of the static input like the 0.1 degree elevation data. What we want to estimate is the underlying 0.1 degree 3-hour multi-source precipitation observation. So here is the study area, and here is the typhoon Lakima. Is the second largest typhoon that we have observed, and these are some snapshots of the precipitation in the hurricane center here. And here is trying to use UNet to estimate the precipitation, 3-hour multi-source precipitation from this half-degree hourly geopotential height, wind, humidity, and temperature. Those are the resolved dynamics. And we can get pretty good results regarding correlation and root mean square error. But as I mentioned, it's far from enough. And what we want to do is that given this kind of closely resolved geophysical fluid dynamics, can we know the probability distribution of the underlying fine-grained precipitation? And we hope to maximize the conditional likelihood of all the observations to give us the good model for estimating precipitation. And I will first introduce some baselines here. The first baseline, I think there's a paper published in James from Tim Palmer's group, and they're using, they compare the two baselines here. The first is conditional variational autoencoder. So if they try to learn this kind of conditional generative model, where X is the resolved geophysical fluid dynamics, Y is the precipitation observation, what they did is they dissect this log likelihood into these three components. The first two terms are called evidence lower bound, and the last term is the residual term. So what they did is they maximize this elbow term to implicitly push up this log likelihood term of the generative model, and is deeply rooted in the statistical learning theory. And what they did is that they have a prior distribution like standard Gaussian, and they have the distribution they want to approximate. So they try to find, so for each sample here, there should be a corresponding sample here that gives rise to this realized sample. And all the samples here should take the place of all the prior here. So these two terms basically like quantify these two requirements. So that's what convolutional variational autoencoder did. As you can see that we are learning two models at the same time, the encoder and the decoder. When we're trying to do sample, we just get some random seed here and put into the decoder. So hopefully we can get an unbiased sample here. And the other thing, which is kind of more popular, is called conditional GAN. So what GAN did is that they try to approximate a probability distribution by forming a two-player game. One is the discriminator, the other is the generator. And we try to generate the try to approximate the distribution of all the cast images. So what we did is that we have a pseudo random generator. It might generate like 100-dimensional standard Gaussian, and put this into a generator. The generator will give something that does not look like a cat at all. And we'll have a cat here from the true data set. The discriminator trying to say if it's true or fake. Then the discriminator says that, well, definitely this is fake. And the gradient here will be reversely used by this generator. So we can make this a little bit better. And finally, we have we can turn this standard Gaussian into some like really good looking cat image set. And DeepMind apply this for the precipitation nowcasting problem. They have a like regularization term here. That is, all the samples generated here, their mean should not be too different from the reality. And if we are familiar with the probabilistic forecast field, we know that this corresponds to the CRPS objective function. So those are the two baselines here. But how can we do a diffusion model? So what is a diffusion model? A diffusion model is kind of a new generative modeling approach. And what they did here is that they have a target distribution of Y. Y is some potentially high dimensional random variable that we have a lot of samples. And we want to approximate its probability distribution. So what we do here is that we develop this diffusion function. So they are all the sequential of latent variables where we have the alpha t and sigma t telling us how for different time the z should be like. So alpha t is a monotonically decreasing function of time. Sigma t is a monotonically increasing function of time. And at time 0, alpha t equals 0, sigma t equal, at time 0, alpha t equals 1, sigma t equals 0. So we have the original samples. Here I'm using the MNIST as an example. And at time 1, alpha t equals to 1, alpha t equals to 0, sigma t equals to 1. So we have standard Gaussian samples. And we can have this sequential of latent variable that drift y into some standard Gaussian. And we can dissect the log probability of y into this formula. Is really similar to variational autoencoder. And if we have alpha 1 equals 1, alpha 0 equals 1, alpha 1 equals 0, and sigma t is the same thing. So we know that this one is 0, this one is 0. So all we need to do is to minimize this one, and we have an analytical form for this thing, and we have a neural network parameterization term for this thing. So what we did is that we now have this thing as an analytical form, and we can do standard stochastic gradient descent to lower this one, so to maximize this one. And after this, we plug all the learned neural networks to go from standard Gaussian step by step to the original samples here. So that's diffusion model. And we can have different perspectives to describe this model. One is to estimate the gradient of the log likelihood, also called the skull function. Why do we estimate the skull function instead of just directly maximize this equation? That is, if we use a single neural network to approximate this one, then we have a regularization thing. That is, if we integrate over all the potential state of y, it should equal to 1. But that greatly lowers the expressiveness of deep neural networks. If we just approximate the gradient of the log likelihood, we can still push this upward. And meanwhile, we are not constrained by this like integration regularization anymore. And we cannot do it directly because in high dimensional space, usually most of the spaces there is no data there. So we do not know the exact gradient of this log likelihood. And we can add noise. So after adding noise, after changing all these score estimators, we can have a same thing like here. And Yang unified these two perspectives using the stochastic differential equation perspective. That is, we have a target probability distribution. We, like this typhoon here, we drift it toward white noise. And for every SDE here, there is a reverse SDE. The only thing you need to do is to estimate the skull function, which we can use the Fisher divergence or like something like it here to estimate the gradient. And then we can use standard SDE solvers to get us to go from the standard Gaussian to the random variable distribution here. So those are the three perspectives. So how can we implement this model? It actually turns out to be pretty simple. And the power is to repeatedly apply a neural network to estimate the gradient of the log likelihood of the target distribution. And after we train all these models, we chain them together to have so that we can go from standard Gaussian to the target distribution. And the neural network is a time-dependent unit. We have a target random variable sample, and we add noise to it to come to arbitrary time step, and we try to recover the noise. And we encode time in this manner, which is recommended in Yang's paper. And we calculate the Fisher divergence. So for all those steps, after we do all the training, like takes, I think, around 10 days for our problem here, we can get the probability distribution, like probability of y. If we want to get the probability distribution of py given x, where x is the resolved geophysical fluid, we use the control net idea. And the control net is to attack the condition here using a zero convolution manner to attach to these noisified samples. At the very beginning, it does not take any effect, but after training, it will learn how this condition influence the final distribution. So we get Py given X. And as we are estimating the scale function of this model, we can flexibly add the strength of the condition. If we use Bayes rule to dissect this equation, Px given y, you know that it's a gradient of Py log Py given X plus gradient of log Px. So we can flexibly control the condition strength. And here are some samples. This one comes from variational autoencoder. This one comes from GAN. And we see that there are a lot of very good looking samples, but it interpolates something that we cannot recognize. And here is a sample from diffusion. And here is sample from reality. So we can hardly distinguish the samples here and samples here. Some samples from GAN is good, but not all of them are perfect. This is about sample quality. And about sample distribution coverage, we can use similar idea of how we rank different generative models. And if we generate all these figures here, and we try to have a pre-trained classifier to tell if it's 0, 1, 2, 3, or 9, then we can have a class label for them. And we generate like 10,000 samples and see how many is 1, how many is 0. So we get this distribution. And we can see that the raw sample distribution and the diffusion generated sample distribution, they are pretty similar. While for VE and again, they have something called mode collapse. That is, they overestimate the samples for part of the modes while underestimate models. And here I'm showing the results for using diffusion models to estimate precipitation. And here is for the whole field. We can generate ensemble predictions for precipitation, like using VE, GAN, and diffusion. And we have different ensemble members. We can increase the member from 1 to 46 to 64. And we have a single parameter helping us guide how the predictor influences the predictant. And this is evaluated as 0.1 degree, and this is upgrading it to like 8 degree.
Baojiang,
and a very
can I ask a question?
Yeah, sure.
Sorry for interrupting you. Just can you remind me again what the exact setup here is? So you take, is it like what you showed in the very beginning, where you take a bunch of basically GCM variables,
Yeah.
and then it's this one. Yeah, okay.
Yeah, it's here. So the problem setup is as follows. We know that the GCMs can very well resolve the geopotential height, wind, humidity, and temperature at different pressure levels. And we know that their precipitation is not good. So we have the reanalysis geopotential height, wind, humidity, temperature at different pressure levels as our input. And given this input, we want to have a generative model telling us what would the underlying precipitation field look like. And it's a conditional generative model. That is, given same input, we want to know the distribution of this underlying precipitation. And this can be taken as a single sample that is realized by Mother Nature. But we know that if it's just half degree geophysical fluid dynamics, the underlying precipitation might not be unique. Of course, because we do not know the whole the fine picture.
Yeah, of course.
And what we did is that we have a sliding window here, trying to take samples. And this sliding window would get the geophysical fluid dynamical field and get the corresponding precipitation underlying it, and trying to maximize the Fisher divergence. So after we do this,
but this is sort of within one time step, right?
Within one time step, there is no prediction here.
Yeah.
But you can always use the predicted the geopotential height as forcing to and then use this model to give you some predictions.
Yeah, basically. Cool. Great. Thank you.
Okay. So, and what we are evaluating here is that we have a test period where the model has never seen this data before. And the model takes into input of all the result field and try to generate, for each result field, generate 64 samples, 64 ensemble members. And we calculate the correlation coefficient and root square error scale of these models, like with different conditioning strengths for this diffusion model. And here is the average correlation coefficient. And here is at 8 degree. The black line is a UNet result. So UNet is like trying to do deterministic forecast. We know that it should do good at the resolution that is trained on. But if you look at here, our model far surpass the CNN the UNet model regarding a deterministic scale. So this is pretty worth celebrating, which means that even if you are you train the model on 0.1 degree, if you upscale these predictions, this is the only model that can surpass UNet. And this is a general scale evaluation, but I'm showing you something more interesting here. Is I show you the typhoon Lakima here. And we all know that is the trajectory is here. I take 10 snapshots, and those are the 9 of them. And you see that it's pretty extreme precipitation with a characteristic typhoon structure here. And if we have the resolve dynamics as the input here, those are observations. And we take into input of the resolve dynamics and take them into a diffusion model. And we get this kind of precipitation estimation results. And if you use the method developed by DeepMind, their precipitation nowcast paper, although they are doing nowcasting, you can use them for downscaling, taking into input of the same input that we have here and try to estimate the underlying precipitation. You get it here. It looks like it has scattered results, but you cannot capture the whole structure. Maybe it's because the model structure that we are using is a convolutional neural network. But I think that if you want to have this to produce this kind of well-organized structure, you need to have some sequential generating process, which is only diffusion model now has it. It's like cellular automata. You keep applying a theme or similar rules to a single pattern, and you get the whole picture. And diffusion is like a trainable cellular automata here, and it get very good results. This is a single sample, and this is for GAN. This is for VAE. VAE is a good, theoretically very good model, but in reality, if you try to train the decoder and the encoder together, and you try to sample using the decoder, you get this kind of blurry results, just like UNet. And UNet severely underestimates the precipitation, while the diffusion model shows currently the best results. We do have the wolf simulation for this particular case, but I don't have time to put it here. And the diffusion model generates much better details compared to wolf. If you configure the wolf to like 3 kilometer or even 10 kilometer resolution. And here is where I'm showing all the samples, all the 20 samples generated for each case. So for this case, you can see that these are our generated results, and this case are our generated results. And you can see that we are basically following all the patterns while giving a lot more diversity here. I haven't very carefully examined the probabilistic scale score of these models, but based on my experience, I think it's kind of a shock to get this kind of good results. I can see the patterns here, they are all there, and the extremes, they are all there. So basically that's all the results that I have for now. And I think a good in climate science, due to the high dimensionality and due to its chaotic nature, we should definitely turn to generative models or probabilistic models to make all the tasks that we used to do relying on dynamical modeling or supervised learning. And I think we can have, if we have a really good probabilistic model, we can do a lot of things. Like if we can accurately estimate the high dimensional data, a PX, then we can quantify what is climatology. Climatology is not about the mean state of the climate system. It's about every order of moments. And in climatology, we also mean that internal climate variability. If we can have a good generative model, maybe we can take use of all the existing climate simulations without running them again, without doing like such burdensome data analysis. And if we can have a really good high dimensional distribution estimation, we can have better data storage because the data structure informs us how we can compress those data. And we can benchmarking predictability. If we know the spread of a possible climate state and given observation of some initial state, we know if we are having some predictability. And if we can flexibly inject the conditions, we know maybe we can do better data simulation. So if we can inject the observations into the state estimation problem, or we can do probabilistic forecast, and we can do detection attribution. That is, we have Y as external forcing. Different external forcing may change the climatology. And we can do flexible domain adaptation. That is, if we change the model state, maybe we can have better models, or maybe we can do better climate change detection attribution and forcing climate sampling. So I would like to end with this picture here. And Van Octop have this fascinating tutorial about how to draw a horse. First, you draw 2 circles, you draw the legs, you draw the face, you draw the hair, and then you add more details. You get a horse. 4 to 5 used to be a joke because that people think that this is the most difficult part. But with stable diffusion, you see that 4 to 5 is no longer a joke. It's possible now because we don't even need a lot of pair data to get 5 from 4. And in developing climate models, first we have a simplified dicole that's trying to resolve a simplified version of the geophysical fluid dynamical equations. And then we have a full dicole, and we add parameterization. We add more parameterization. Nowadays, people are developing some concept called climate digital twin. I used to think that's a joke. That's a renaming of the existing technique. But with these probabilistic deep learning techniques, I think from 4 to 5 is a viable way. And I think it can benefit from the lesson we have in the left, 4 to 5 diffusion model. Maybe here, 4 to 5, we can also use diffusion model to do it. And here I just explained a very low hanging fruit of downscaling or super resolution of climate models. But if we recall the paper of like using adversarial learning to align the climatology of reality and simulation, the paper are published in James, and the paper, a similar idea published in Nature Machine Intelligence from your group. Maybe we can achieve much more in a much quicker pace. So that's my hope. And that's all for today. Here is a QR code for my YouTube channel. So you can see in my previous videos there. And here is the logo for my research group. We have the reality, we have the simulation, we have a Mobius band connecting them together. And I hope probabilistic deep learning is the channel here. Yeah, with that, I'm looking for questions.
Thank you very much, Baojiang. that was extremely interesting, and yeah, a very, very good fit to what we also have been thinking about and what we have been working on the last 1 or 2 years. I have a few questions, but maybe others start. Are there any questions?
Maybe I would have a question.
Oh, sure.
Yeah, thanks first of all for this really interesting talk. That was very inspiring. I was wondering sort of what the lead times is for the forecasts for which you show the results. Is it sort of in the weather forecast range, or is it more like short-term, medium range, or longer? I think I missed that.
There is no forecast here. It's just you have the geophysical fluid dynamic field here. Like you go past 3 hours, go forward 3 hours, and the current 3 hours you use this 9 hours to estimate the middle 3 hours precipitation. But you know that we have numerical weather prediction. They have pretty good geophysical fluid dynamical estimates for the coming 7 days. You can plug this model into these models, into the NWP models, and use them to generate precipitation. We have a paper published in 2019. We train a very simple convolutional recurrent neural network to estimate precipitation, and we use ECMWF subseasonal forecast to their result field to force the trend and get a precipitation estimate. So that one has better room square error and correlation to reality compared to their original precipitation forecast. And we even force a hydrological model using these 2 different sets of precipitation products, one from data driven and the other from like process driven. And we find that data driven shows a big advantage there.
Yeah, sorry, I was referring to the physical model, not the machine learning part. So this, I think you're using simulations from the CFS.
No, yeah, we are not using simulation here. We are using the reanalysis because we want to have paired data.
Okay. Yes. Okay. Yeah. Yes, that answers my.
Yeah, but we do have some students trying the nowcasting thing using diffusion model, and I think the results are pretty promising.
Mm-hmm.
And I know that many people are doing these things nowadays. The field is changing so fast.
Okay.
Yeah, I agree. It's very rapid. Baojang, about sort of turning this into forecasting, there's of course a certain error in the, let's say, I don't know, whatever your favorite forecasting system. If you take IFS, then of course, I mean, sort of we were suffering from this problem as well, that if you do forecasting, you take the climate variables and then, you know, like pressure and the relative humidity and so on. And then basically you do a final post-processing to get the precipitation.
Mm-hmm.
When ideally, of course, so this can only be as good as the predicted climate fields, like geopotential height and so on.
Yeah, exactly.
And they of course rely on the stochastic or whatever kind of precipitation and convection parameterizations that the model indeed uses.
Yeah.
So ideally, one would like to do exactly what you showed us, but not just as a final sort of offline post-processing, but to do this online in each step, right?
Exactly. That's why I call this a low-hanging fruit. I need to finish this as soon as possible.
We had the same situation.
Then, if I'm doing like online coupling, it might take another 1 year, and these things are no longer new at all. And I think this kind of paper would come out if it's not done by me, it's done by someone else, maybe in like 2 or 3 months.
Yeah, I agree.
Yeah, and I agree that to couple them with the dicot is the most difficult one, and I think maybe we do not need to follow what Mike Pritchard did. I mean, you might not want to develop a polarization scheme offline and then try to couple them back to the dicot you have the domain shift problem. They are not stable there, but you can always do it in an adversarial learning problem setup. That would be something huge. Do it. You couple it with the DICO, but you do not learn offline. You learn it online. That's the power of adversarial learning.
Yeah. Yeah. Okay. Great. We exactly agree on that. And maybe from your perspective, I mean, you showed us several examples, and like looking at the pictures, then it's sort of, I mean, the whole diffusion hype and these pictures that show that diffusion, the transformation of diffusion models work better than GANs. There's always sort of, I have a feeling, a bit of a selection bias here. Here it's clear.
Yeah.
That's your result. But what I would be interested in more, so I mean, it's very convincing. That's not my point. But from a fundamental perspective, how would you explain that diffusion models, and maybe, I mean, in particular spectral diffusion models, work better than GANs?
Okay, so the reason why GAN here is not so good is that we are using half-degree circulation field to estimate 0.1 degree precipitation. So if we use 0.1 degree circulation field to estimate 0.1 degree circulation, it would be much better than here. The condition information is offering too low information content to our final predictant. And that's why I'm not learning very well here, and it's not so stable. So GAN is not so stable. I can just train it like this, and maybe if you force me to train it again and again, I can get some better results. Here I'm just using it as a baseline. I'm not tuning it to a very deep level.
Yeah.
And the reason why I assume diffusion model is better, and actually is better, is that it's really like wolf. Let's see how we use dynamical downscaling to get a half-degree circulation field to 0.1 degree precipitation. We have a discretization of this half-degree circulation field using bilinear interpolation to get 0.1 degree initial field of wolf, and we run wolf. We update the state every few minutes. Like if in 1 minute we update the state. And then we get the final results of 3-hour average precipitation or accumulated precipitation.
Hang on, you have to explain. I have to go a step. Sorry, you lost me. Maybe okay. Just for everybody, WRF, WRF is a dynamical, like a regional climate model used for dynamical downscaling typically. But I didn't understand. Do you actively use WRF here, or do you?
No. I'm not using WRF. I'm trying to replace WRF.
Yes.
I think this method can replace WRF.
Yeah, exactly. That's what I agree. But what is the reason why okay. That might work?
Why
you follow the WRF strategy, or
no? I'm following the meta strategy of WRF. What WRF did is that they discretize the initial field into a fine resolution, and they keep updating it. They spin it up. They keep updating it step by step. And what diffusion did is that they have a totally random initial field, which is of high resolution. If they want to mimic some samples, they use, here I'm using 1,000 neural network to generate a single sample. And each neural network work step by step to refine the sample. So it's truly generative. It's not a single step, like go from latent to the result. But diffusion here is that you want to have something, you get the condition And you use this condition to control 1,000 steps of how you get the final result. And a wolf, if we try to simulate a 3-hour precipitation, it uses like 3 hour, every minute it updates its state, and in 3 hours it updates for 180 times to get the final estimate. And that's the inductive bias of repeatedly applying a process to get the generated result. I think that's the biggest power of diffusion. Now we finally can learn to generate a complicated thing in many different steps, not only one step. If it's one step, I think GAN has get us the final result. GAN and CVE, they are just a one-step generation. Like from the 0.5 degree thing, generate this. But diffusion is like from 0.1 degree noise, apply the neural net 1,000 times and get this.
So you think that so actually for the bias correction task, the cycle GAN might actually work just well. Your point is that for the additional challenge of a downscaling, that's where the diffusion model really excels, because that's what the GAN couldn't, because it wouldn't have sufficient predictive power.
I think even for the bias correction task, cycle GAN can work well. But just imagine how well can cycle diffusion do.
Mm-hmm. Yeah.
And that's something I want to cooperate with your group. I know cycle GAN is great. It's an unsupervised way for improving climate models, trying to align their climatology of simulation and observation. But it's still of same resolution, right? Observation, it has a lot, the entropy of observation is much higher than simulation. And if this blocks the way of how we can train cycle GAN to a very fine detail. So the way we should do is to blur reality, to lower the information content while trying to denoise the simulation altogether. And then you get the bias corrected probabilistic forecast with really fine detail. Or put it another way, you get a digital twin.
Mm-hmm. Yeah, I agree. I'm just wondering, so I mean, I have seen GANs, like not cycle GANs, but I've seen GANs. So in principle, so I really like how you say you use WRF as a sort of as a meta strategy for what you do here.
Mm-hmm.
So with GANs, you can also transform noise into, I mean, sort of what you explained in how you use the WRF meta strategy for your diffusion model. There, I don't see the sort of fundamental difference because I could do that with a GAN as well.
Yeah,
right?
you theoretically you can do it with a GAN, but practically in a machine learning problem, there are always three kind of errors: statistical error, approximation error, and optimization error. Statistical error means that if you have limited data, you cannot learn well. Approximation error means that if the function space is not good, you cannot learn well. And optimization error is that if your optimizer is not good, you cannot learn well. And the problem with GAN is that the optimization error can be pretty big. So which means that you cannot optimize a very good GAN easily.
Yeah, you might get one by chance, but you cannot do this systematically. Yeah, okay. Yeah.
Nobody can say that they have the perfect GAN training strategy. But for diffusion, it's a different story. You have a single objective function. Just buy more GPUs and pay the bills and then just keep running it. Really stable.
Yeah.
So very little optimization error, very little approximation error, because it's trying to, if each state they have some optimization error, have some approximation error, which means that the function space is not good. You are applying it 1,000 times. You are canceling all these approximation error. Like for GAN here, you are relying on single neural network. The approximation error might be really big. And both these methods, they suffer little from statistical error.
Yeah.
Because they can keep shuffling.
Maybe if I may, another rather trivial question. Does it help? I mean, this is really just out of curiosity. So in your setup, in your can you, if you take the precipitation estimates from the same data set, from the same reanalysis data set that for which you use the geopotential height fields and so on,
what
do you get? So if you would, in the dynamical input, if you would take the precipitation of this data set, would that help at all?
Nope.
I
did an experiment. I didn't do this experiment, but I did another one. That is, you have the model simulated geopotential height, and you try to use it to estimate the model simulated precipitation. It's almost 100% accurate.
Yeah, okay.
Yeah,
then, okay.
those models precipitation are just some functional functions of the resolved field.
Yeah, of course.
Yeah, so they are not helping. And if you take the precipitation here as input, I think the scientific advantage of this model is not as high. Because here I'm just using the geopotential height, wind, humidity, temperature. They are the 7 variables. Here. And just these variables, just from the dicole.
Yeah, although of course, as I mean, following up on my question in the very beginning, there's of course that issue that in practice they do rely on the precipitation parameterizations inside the model from previous time steps.
Yeah.
Right. So if I understood correctly, this is not written up yet, right? So you don't have anything, any paper on this.
I'm having a paper. I will submit the preprint in a few, hopefully in 2 weeks.
Well, okay.
Results are ready. I think it takes 2 weeks to train the model, so I'm not worried that to show the results.
Yeah. Okay, interesting. I don't want to take all the time for questions. Does anybody else have further comments or questions or remarks?
Yeah, I would like.
Okay, Michio, please.
Okay, I wanted to ask how is the inference time when doing the diffusion models?
Well, if you just use the Euro DDPM, it's 1,000 more expensive than GAN. But there are things are changing so fast. Last week they can do it in 1 step. They first learn 1,000 step, and then they reduce them to 1 step. 3 months ago, they reduced it to 50 steps. I'm using the DDIM idea, the Northern Diffusion Implicit Model, 50 steps to get these results. But when you are training like infinite time steps, because I'm using the continuous time. So T from 0 to 1, and you can sample T from 0 to 1, infinite time interval.
But GANs like still have a huge advantage there in this perspective.
Yeah, even if it's 1,000 times, it's still much faster than numerical modeling. No, that if you want
And
to do, yesterday I just learned that if you want to do a global 3 kilometer simulation relying purely on GPUs, you need to run 10-day simulation, you need 2,400 GPU hours,
mhm.
which amounts to $2,000 of computing fee.
Yeah.
But here it's just a single GPU, you run it, and
Mhm.
for like 1,000 times, you get a good sample. But it's just for simulate for parameterization now. It's the low-hanging fruit. I believe many more exciting things are coming.
And
Do you believe both in the weather forecasting? Sorry, just as a follow-up question, do you believe both in the weather forecasting and in the climate modeling, or do you focus more on forecasting, let's say on from nowcasting to medium range or even seasonal?
I believe seamless forecast. I think all forecasting problems they can be in this framework. Systematical bias, internal variability noise. In weather forecasting, internal variability noise refers to the state estimate noise, state estimation error. And we do not have a lot of forcings. And in seasonal forecast is the forcing from the ocean, from the stratosphere. And in climate forecast is forcing from greenhouse gas. I think this single unified framework can help us to do a unified seamless forecast.
Sorry, Michi.
I think
yeah.
Go ahead.
I wanted to ask if you have thought about working with like when we talk about cycle GAN, and we have 2 data sets, and like there are publications about also diffusion models utilizing a similar approach where you train for example, one diffusion model for encoding a data set and then another one for decoding and do like the cycle GAN translation in this way. Or like I think there are several architectures that try to do something similar.
We have a cycle GAN paper published 2019, and it's not a simple cycle GAN. Only cycle will not help a lot. The basic idea of cycle GAN is to develop an isomorphic mapping between 2 dynamical systems. And you can add different constraints to foster the training process. And in that paper, we have 3 different regularizations, and we force the model to match the climatology of reality. And we think that's a different way of climate model diagnosis compared to the 2 common ways. The 2 common ways, first is to do weather reforecast. You initialize the model to match the state of reality, and you observe the trajectory difference between reality and model at weather scale for 7 days. And the second is the climate forecast. You force the model to run 150 years with same forcing, external forcing, I mean the radiation. And then you have, you observe the past climate, and you try to see the difference of their climatology mean and different statistics. Why we do that is because it's a chaotic system. We cannot force the reality and model to follow same trajectory without extra forcing there. But I think with cycle GAN, all those kind of domain adaptation methodologies, we do not need to do control experiment anymore. Weather forecast, climate simulation, they are all control experiments. You try to control the external forcing, and you try to control the internal variability noise to expose the model bias. We don't need to control the internal variability noise. We know that there are some intrinsic feature of this system. We just have their 2 state space being identical. And I think that's the only way we can reach a so-called digital twin. It's indistinguishable.
Yeah, but I mean, like, did you try to work on like a diffusion architecture that is like a similar setup to the cycle GAN, where you do, for example, unpaired image to image translation.
Well,
But that's exactly what you said earlier, right? Cycle diffusion, basically.
Cycle diffusion. That's what I said earlier. But I think many people may think of this idea sooner or later, and the two groups that may come up with this idea is your group and my group, and maybe we can collaborate on this idea if there is an opportunity.
Yeah, I think that would actually, I would be delighted if we would go towards that step. And I guess it would make sense to do that. Maybe it would make sense to do it in a first step in a sort of like in a similar setting like the James paper that you were referring to by Philip, where we do it for like a short-term climate prediction, weather prediction setting. But
one thing, I wonder if you have tried, if you do cycle GAN for climate model bias correction, and you apply this to that climate model for weather forecast, it's actually more accurate than the previous weather forecast.
The problem there is that sort of, like climate models, I mean, it's the same GCMs historically and conceptually, but the models that we use for climate predictions, you can't use them for weather prediction anymore.
Now, then let's go to CFS. Let's go to seasonal forecast. Let's apply cycle GAN to seasonal forecast.
That would be something that I would find very interesting, yeah. But
that's what I did, and it will be submitted to James very soon. So you use cycle GAN to bias correct seasonal forecast, and you see a great improvement at weather seasonal scale, indicating that it's actually correcting the bias, not just correcting the statistics.
Yeah, that is very interesting. But the idea would be, so you use cycle GANs for that, and not a diffusion model.
Not yet, and I think that's something we should do.
Yeah, maybe that would be something very interesting to do together. So I think this is also what I've been proposing to you, Yuang, to look at seasonal timescale for prediction, and to use generative models for that. So maybe that could be something where we could work together. It has the advantage that it doesn't suffer from the problems that we have in a climate modeling context with all the out of sample issues that we have there, which I think are solvable, but sort of isolating the problem first and having that part outside the first problem, that's probably a good approach. I had one more question, but I forgot. Yeah, so so we are at the PIC Potsdam. We're developing an Earth system model called POEM, and together with the developers, we are actually sort of trying to establish such an online version of this. It's of course very tedious because the model is written in Fortran, and so the atmospheric model is an older version of the it's AM2, Philip, right? I think, yeah. But so there we could also talk about that. But maybe before we go into too many details, maybe are there any further additional questions in the audience at this point? Maybe there was one question by Lei Wang.
I think see in the chat box.
Yes.
Diffusion flow.
Yeah, exactly.
Right. How to accelerate the process if speed is critical, like permutation. There's something called last week there's a paper showing how you can do one-step diffusion for sample generation. As I say, this field is like, it's amazing. It's no longer slow.
Very interesting. Mm-hmm.
I think it's called concurrency model. It's from the author of the SDE diffusion paper.
Mm-hmm.
Yeah, he's now in Caltech.
Maybe, sorry. Thank you, first of all, for the really nice talk. Just a very small thing to add about the atmospheric models possibilities. Also, just mentioning that speedy weather is also slowly approaching a state where this could be usable for something like this as well.
Yeah, exactly.
Milan made a lot of progress with this recently. It's not quite there yet, but for like this whole online approach, this might be still easier to convert than the poem atmospheric model.
Mm-hmm.
Yeah. Yeah, maybe then if are there any further questions?
Oh, I have a question.
Go ahead.
I want you just introduce that you would like to use diffusion model to replace the wolf, but we know
Yes.
the wolf just like this this figure. The wolf if we give different initial permutations to the wolf simulation, the wolf will output different trajectories along the time.
Yeah.
Then at that time, in this case, diffusion. I know diffusion can also generate such a different trajectories. Among these trajectories, we can use Lyapunov index to or aerial growth rate to estimate the how much the trajectories will be divergent. So do you ever do you ever test the compare wolf and diffusion, how the trajectories will be divergent differently?
That's a really good question. I said that I want to replace wolf not to be as good as wolf, but to want to be better than wolf. Wolf have a lot of problems. The thing you mentioned is that the trajectories might diverge due to two reasons. One is the initial state, and the other is the parameterization choice. And the divergence due to initial state is aleatoric, and the divergence due to parameterization is epistemic. We should not mix them together. And if we want to see if the diffusion is creating meaningful divergence, I think I would consider your idea. But the first step I do is to compute the probability prediction scale of the model, like compare wolf and the diffusion model.
Yeah.
And I think the good thing for diffusion model is that it does not need to run an offline dynamical downscaling. It can serve as a super parameterization and direct couple with GCM.
Yes.
And also, like if you run wolf, you have the outer trajectory given by the coarse resolution model, and the inner part is from the fine resolution model. After like 4 or 5 days, the two states are not matching.
Yeah.
And you cannot tell which is good, which is bad.
Yeah.
Because the final might not be accurate. The cursor might not be accurate as well. You don't know which is good. But what you want to do is that you want the inner state to match the outer state while still being accurate. I haven't get an exact idea how to do that, but I think the diffusion model shows some potential to surpass wolf.
Yeah. Perhaps we can perhaps it is possible to calculate the Lyapunov spectrum for diffusion model. Like
it's possible. It's possible to do that. And I don't have that background. I don't have that knowledge, but I think that's a meaningful step.
Yeah.
That maybe we should consider later.
Yeah.
First, pick up the low-hanging fruit.
Yeah, but the low-hanging fruit, it seems you have already, I mean, you're going to pick in 2 weeks then. Because I like Yu's question a lot, because I think that calculating the Abner spectrum of the sort of diffusion model ensemble and comparing that with the WRF ensemble would be really interesting as a sort of diagnostic, because, you know, in the end, you can always say your model has higher accuracy, but you can do this, of course, in a weather forecasting, because you have paired samples.
Yeah.
But then as soon as you go into the climate prediction or climate projection context, you don't have paired samples, and it becomes increasingly challenging to benchmark whether your method is better than something else. And in particular, you know, and looking at the Lyapunov spectra of the ensemble of ensembles is a really nice way to sort of gather more information on sort of like how the chaoticity of the system, of course, and that you could use this information to diagnose why, even in the paired sample case, you could use it in a first step to maybe understand why your method then produces better results than WRF or not.
Yeah.
So this is sort of like as an in-between step for model diagnosis, basically. I think this would actually be really interesting. You.
Yeah.
Good point.
Yeah. Yeah. I think that's a very good point. Yeah. But I don't have that knowledge. I think that's a reason why collaboration is promising.
All right. Any further questions to Baojang? Okay, then thank you very much again. This was, I mean, yeah, extremely interesting. Really, very much appreciated. Thanks for taking the time to show us your work. If you like, then we can maybe with Michi, Philip, you and Max, maybe we can stay a bit longer and discuss a few more details of sort of seeing whether we can set up a collaboration. But in general, then I would suggest that we thank Baojang again, and everybody else have a lovely, well, we're all in different time zones, so have a nice afternoon, have a nice evening.
Thank you.
And so on.
I can leave, right?
If you want to stay for a bit, Baojang, to discuss a little bit further, then I
sure,
would be delighted.
Sure.
I was mostly suggesting that we don't bore everybody else with more detailed discussions. Oh well, we have a few more spectators, but I guess that's fine. So yeah, I would be really, really happy if we would do something together. And comparing, so you said that so your version of the cycle GAN that you described, that is about to come out in James.
Yeah, we're preparing. I have the code, and I was preparing it before coming back to China, but no family issues, and then just postpone it. Yeah.
It's not submitted yet.
No.
Okay. I thought it was about to come. It was about to be published.
No, not yet.
So because it would of course be very interesting to use a diffusion model for a similar purpose on seasonal timescales, and maybe that would be something that you could. I mean, that would fit very well to the plan that we already shaped you. To use generative models for seasonal scale forecasting. Yeah. So maybe that could be one thing that we focus on first.
Yeah, sure, definitely. I have some primary results, and I was about to do that one, but then I encountered diffusion model. I just put on that one. I know that this would be the future.
Yeah.
And once I've finished this like downscaling paper, I will go back to that generative model for seasonal forecasting. And I think that's a good starting point.
So if you would be up for collaborating there, that would be really interesting.
Yeah, definitely.
And then, because I think that's still seasonal prediction is still considerably easier. So let's say the set of conceptual problems is smaller than for climate projections.
Yeah.
Yeah. Because, you have paired samples and so on.
Yeah.
So yeah, that would be, I would be delighted if we could go in that direction. So do you want to, what would you need for getting, what would you need to get this started?
Yeah.
Wrong.
Yeah, but currently, for my first step, I just consider I am just considering if I use global data sets to make the S2S prediction, I should first to predict the spatial distribution or just or only forecast a single oscillation index like NAO index. Yeah, this I know this is different. If I use diffusion model, I can use the global data sets to make the spatial distribution forecast. But if I use if I use CNN or FCN, I can only make prediction for some single time series. Yeah.
Yeah, I think that is different from what we have in mind here. Here, it's really about predicting the spatial fields, and doing that with high accuracy.
Yeah.
Yeah, but I think that would be, so if that would be really sort of also in your interest, Baojang, to collaborate on doing really precipitation forecasting on S2S timescales. That would be really cool.
Yeah, I actually I'm doing previously I was doing it for CONUS for US, just US, and I think maybe we can do a global forecasting system.
Yeah, I think it would. I mean, in some sense, it's easier, right? If you have the computational resources, then it might make the problem easier.
I'm trying to gather
guess.
some money to buy some computing here. Yeah.
Yeah.
Yeah,
it's very complicated. Like, we have this issue that so we wanted to buy a DGX H100, but the problem is we can't figure out who will pay the electricity bill. And it's just, I mean, it's not negligible.
Yeah, it's huge.
And yeah. Let's see. Okay, very nice. I was impressed, Baojang. Very nice work.
Maybe sorry, I have some technical problems today with the internet connection.
Sure.
But because I was training this gun for an online correction of precipitation, and it's been struggling a bit. So I guess I would be interested also how the cycle diffusion method would work.
Well, when you train GAN, the very often you face the problem that the discriminator is too strong, that it's not offering useful information to the generator or to the bias corrector to improve.
Yeah.
And when you are doing diffusion, you kind of blur the true and fake samples. So if you blur them, you pose a more difficult task for the discriminator. And then the discriminator is no longer so strong. It offers you some, if it's not so strong, it can teach a weak generator or bias corrector. And then you chain them together.
Do you do this only in the beginning?
The thing with cycle GAN is that it's not injecting meaningful noise into the bias corrector. You prefer some distribution, like those resulting from stochastic parameterization. There's a paper from CMU they did something like they have the bus character or the generator equipped with a variational autoencoder. But all those things, they look like a primary version of cycle diffusion. I think the thing we can do is that we first set up a cycle GAN baseline for seasonal forecast. Then we have like stable diffusion 2.0 to beat the cycle GAN.
Yeah, I think that's the natural setup. I agree.
Yeah, and then if that's a strategy, we might match not just focus on cycle GAN, but while we are doing cycle GAN, we go to the field of cycle diffusion.
Yeah, yeah, exactly. And sort of, I mean, if we realize that in that context, then training the GAN is tedious, and we don't really have convergence, and we have a too strong discriminator and so on. We might even abandon that, because the risk is, of course, if you only want to use the GANs for benchmarking, and then you spend way too much time in trying to get that benchmark to work, then it's, I mean, at some point it's just a waste of time, I guess.
Yeah, it can be a waste of time if they come up with a better model.
Yeah, the problem is really if the training is so unstable, and then you only use it for benchmarking, and then
you can do something from that part. It's a fast developing field. People are talking in different languages. They learn things in different paces.
Yeah, true. That's absolutely true.
Yeah.
All right.
Maybe I have one very not very structured comment, but something that I'm like excited, which I'm like also excited about, just as a comment. With all of these diffusion model approaches, I think these are also could be very suitable for our group, especially because they kind of like move two topics together that we've been working on, because we also have been working on like neural differential equations a lot. And like especially stochastic neural differential equations are used often a lot in the diffusion models, and you also showed this today. So I'm not quite sure yet how exactly we could integrate this, but there's definitely also a few things that we could look into, like using a bit of our experience and knowledge of neural differential equations there. For example, the experiments that we did with them adhering to constraints that Alistair, one of our PhD students, did. For me, it's really exciting, because for a long time this seemed like a bit two different fields, but now this is also more or less coming together.
So Max, what you have in mind is that sort of I mean, you're calling this parameterization, but it's of course what you showed to us, Baojiang, and also what we sort of did with Philip. It's not strictly, I mean, it's not the same as what they do in subgrid scale parameterization stuff, right? But of course, it gives you the same thing. It's just, I mean, it's a much more efficient way. So Max, your point is you have your climatic fields, you have your pressure fields, and so on, and then you just use them to generate a precipitation output for a model. And the question is if we now really need very, very comprehensive, accurate GCMs anymore, or whether the diffusion part can basically, you know, I mean, it might not make the difference anymore if we have a very, very high resolution GCM, or if we have a more approximate, not so accurate, but in turn very, very fast GCM. It might lead to the same accuracy in the final precipitation output you generated by a diffusion model. Is that sort of where this comes from, Max?
Not really. I'm more concerned, like my comment was more on basically the generators or the discriminators of a lot of these setups. They are not strictly just neural networks anymore.
Yeah, they can be differential equations.
Especially stochastic differential equation. So, I mean, in a more kind of like something that you wouldn't, in a more conceptual project, more like prototypical project, you could also look into, okay, how does this actually work if you incorporate some kind of like prior knowledge about the models into the into the differential equations, especially those of the generator. Probably not the discriminator, but if you use the generator ODE or SDE, and if you use these kind of approaches that we were researching for neural differential equations in this,
Nice.
that's something that I would find interesting for more conceptual study. Not something that will yield immediate great results, but more like on a method level.
There's a guy from Princeton, and I think he's coming to Cambridge. Kramer. He's doing those kind of things. He's from field of astronomy.
Mm-hmm.
Can you send a link from that?
I can't remember exactly his name. One moment, let me check Twitter. Miles Kramer. What he did is, yeah, well, let me put in the chat box. So, I think we can always achieve a same destiny following different ways. But the thing that I think most is what's the most efficient way in our limited life to go as far as possible. And I think for geoscience, it has already becoming too complicated to do in a like process-based way. But still we want to have something like symbolic representation. The reason why I'm bringing forward Miles Kramer is that he found some way there. That is, you fit a neural network, you extract the neural network idea, you extract knowledge of the neural network using some symbolic regression and how to optimize that process. There's the thing that shocked me so much is that DeepMind, they use GraphCast and they can do the weather forecasting to such an accurate level in such a few GPU hours. While we have a guy here, he came from GFDO and he's writing the FV3 DICO in GPU, and it takes 2,000 hours to finish a same thing as what DeepMind did using a single hour GPU computation. And I wonder if this is telling us that the computation complexity of the Navier-Stokes equation is not so high, or is not as high as what hand-coded codes can be. I don't know what's the limitation there. That is how you balance computation and accuracy.
Would you say the same still applies to GraphCast? So when they do medium range, would you say the same still applies? Because I've had a chat with Shakir recently on this, and they also said they have even tried to do hybrid. I mean, I mean, on the way when they developed this, they tried to incorporate parts of the physics, and it just, I mean, it didn't help.
Yeah.
Practically I mean, even in GraphCast on a medium range, it just sort of the purely data-driven model outperformed everything that they tried where they put in some physical knowledge.
I think
which I also found very frustrating.
The best thing that might come from Shakir's work is that they do a graph convolution, right? And if they can yield a DICO code from their GraphCast neural network, if they can give us the kernel of the convolution, is that kernel same or have some kind of isomorphic mapping with the code? Right. If they are not, why are they still as accurate Also, maybe the code we write is not deep. It's just single step discretization and like 1 or 2 steps computing if we have some iteration. And their graph cast, they have like deep layers. And I think if Miles Kramer came to that graph cast idea, and they too like trying to understand the neural network in a way of like in a PDE manner, that's really fascinating. I mean that if we can learn a neural network and then neural network give us a discretization of the underlying PDE, I think everything that kind of channeled. You can write it directly, you can do data driven and get to that discretization. I want to see that result.
Yeah, I agree. That would be very interesting. But nevertheless, Max, on the other hand, of course, it's still an intriguing idea, since we now have these, I mean, in this generator discriminator pairs to include what we think is really true physically, to include that inside the generating process. That, I mean, it's still a really good idea, I guess.
Yeah, I think there are two separate ideas also. Either you can include knowledge, or you can do the constraint approach like Alistair is doing. And this including knowledge, I mean, I would be curious what exactly Shakir and DeepMind were trying there. But I mean, like, this is probably, I don't know. I mean, like, I'm still hopeful that like there's some things that are also helpful, just maybe not the obvious low-hanging things, because I guess in data-driven learning, just diffusion or advection data-driven is probably very easy.
Yeah.
But there are other processes which might not be that easy to learn purely data-driven. And on the other hand, especially for climate simulation, introducing some form of like constraints is probably still a very good idea.
For the climate, I mean, for the climate case, one has to build in physics to make sure that all the out of sample problems don't let your problem, that let the whole thing explode, and then you just get nonsense. For weather prediction, that's also, I mean, that's why we're in contact with DeepMind, with Shakir and Sumi and these guys, because they're interested in climate, but they don't really see how with their methods alone, they don't really see how climate projections could work. But yeah, I mean, the problem is, Max, they don't tell you, right? So, I mean, how they build in the physics, as long as something isn't published, they can't tell you how they did it. And they're relatively strict on that.
But we could look into like a bit more conceptual study on trying to set up something with the discriminator. Generator.
I agree.
There's also, by the way, Linus' masterpieces also, like, after brainstorming with him for a while now, also will develop more of it into like this latent SDE framework kind of things, which is a bit similar as well. He will do a little kickoff presentation about this next week.
Okay. Yeah, this sounds really interesting. So how should we proceed? I have to run to another meeting well, at 12, but I have to have 9 minutes for lunch. So Baozhang, how should we proceed? Should we just sort of plan for another meeting and say in 2 or 3 weeks, once you has also had some time and we have sort of played with a few ideas, and then we make a concrete plan in 2 or 3 weeks? Would that be an idea for you? You would also, of course, so we do this, but Max, then Linus, that would be at 4, I guess.
Yeah.
Yeah, that is 4 p.m. CET is too late for you, Baozhang, right?
What's Beijing time for that? 4 p.m. It's
it's
like 1 o'clock in the morning.
I think it's very late. I think it's at the moment it's 6 hours or 9 hours. What is it?
7 hours, I think.
7 hours. So that would be then 7. That would be 7 p.m. I know 4. Sorry.
No, the 11 p.m.
4 would be at 11 p.m. Yeah.
Yeah.
Yeah, that may be a bit late. Okay. So if you're interested in this, then you're absolutely welcome to join.
Okay.
So that would be, it would be the same link, I guess, Max, right?
Yeah, but it is, I mean, I have to mention this is just a proposal talk for a master thesis. There's no, no results yet.
It will be interesting. Yeah.
So, I mean, if you have time and if you're interested, it's, I mean, don't expect too much. As Mark said, it's just sort of the outline for a master thesis. So it's, I mean, it's nothing big, but yeah, I mean, so I'd be really happy to involve you also more regularly in the seminar if you're interested.
Sure.
And otherwise, if you, so then let's
maybe
give it 2 or 3 weeks so that you can also develop some
Sure,
ideas,
sure.
and then we fix another date for a meeting and then we discuss.
Sure. Just let me know. Always here.
Perfect. Perfect. Great.
It was great to discuss with you.
So you are, when did you move to Beijing?
I've moved here for 1 year. My girl is here.
So you now have the whole so you moved when there was still the lockdown and all the complications, and now it's sort of back to normal, I guess, right?
Still dictatorship. There's no normal here.
Okay. Yeah. That's a different story, I know.
Yeah.
I might come. So I'm a visiting professor at Beijing Normal University.
Whoa.
With Zhaoshang Chen. I don't know if you know him.
I don't know him.
And he's the dean of the complexity science department. And he invited me for fall this year. So when I make plans to travel, I will let you know.
Definitely. I'll treat you dinner.
Great, exactly. Cool. Nice. But then talk to you in 2 or 3 weeks.
Great.
Very nice.
Great.
Okay. Thank you very much.
Thank you.
All the best.
Thank you.
Take care.
Take care.
Bye-bye.
Thanks a lot. Bye.
Bye.